Okay, folks, it is time for that topic that you guys love with a big giant heart. It is the best of all the topics. It is the word problems that we can solve. Why are word problems so awesome, you ask? Well, this is actually where we're applying the math stuff to figure stuff out in real life. And that's actually kind of the point of math. It's not necessarily just to answer random, weird, abstract questions. It's also to be able to answer real life questions and to use some of the patterns that we generalize in mathematics applied to specific situations where they, in fact do apply. So all of this stuff, the need for these sorts of functions came from looking at real things. So one of the classic, generally trigonometric types of word problems are going to involve something that happens repeatedly. So things like a pendulum swinging back and forth, a yo-yo that goes up and down and up and down and up and down in the same way every time, where things are not changing. A Ferris wheel that goes around and around and around. Anything that spins around that's circular, that's going to be a good fodder for some kind of trig function modeling. Okay, so what we call a lot of these things, and we're going to be looking at pendulums, this is something you guys look at in physics sometimes, harmonic motion can be represented by what we call sinusoidal curves. Now, some of you physicists might say, but wait, isn't there like air resistance, and won't pendulums eventually kind of sort of slow down because we don't live in a vacuum and they will just keep swinging back and forth forever and ever? All I'm going to say to you for now is, shh. We're going to pretend that we live in a vacuum when we're doing these problems mathematically for now. I believe you will be looking more at practical applications when you get into, second semester physics in university or so. Okay, so a ball hanging from a string is lifted and released to swing back and forth. The horizontal or x displacement of the ball from its resting position is given by the function, which came out a little funny, x equals minus 3 cosine of 2 pi t, where t is the time in seconds. At what times, possibly more than one, between t equals 0, so 0 seconds, and t equals 2, will the ball pass through its resting position? Okay. So what we're going to look at is, the first thing we want to do is we want to try to model this. So first thing we want to do is understand what is happening. So let's draw a picture. So we've got this string here, we've got a ball, and it's swinging back and forth. Okay, so this is sort of the maximum distance to the left, this is the maximum distance to the right, and then the resting position is here right in the middle where it's at the middle. So we're going to call that the rest. Is where it would just be hanging down before anybody decided to start swinging it. Okay, so it's going to go the same amount on both sides. So we're going to call the distance from the resting position x here, x here. This is kind of like a minus x. We're going to define this as being sort of the minus direction, and this as being the plus direction. Okay, so here we have our x equals 0. Okay, so what is this? So let's write down what does our equation look like. So we have x equals negative 3 cosine 2 pi t. So we'd actually like to be able to get some kind of idea of what that graph might look like. So we have negative 3 cosine of 2 pi t. So as in the last unit, so we've got 2 pi is our b. So our period equals 2 pi over b. So 2 pi over 2 pi, which is 1. So our period is 1 second. And that's how long it takes to go through an entire swing. So we move it to the left. It's raised and released, lifted to swing back and forth. And assume our left is our starting position. It doesn't really matter. Okay, but especially because we're modeling with that minus 3 cosine, it means we're at the highest minus maximum. Okay, So the thing that's a little bit confusing here is our x here. We notice this is in the position where y really should be. So this is going to be our y-axis. So we're going to label this here. This is x, our y-axis, just the horizontal displacement, and this is going to be our t-axis. And a lot of these harmonic motion, our x variable is really going to be a time variable because that's how the harmonic motion or the back and forth happens, is time is changing and something is going back and forth between two different positions. So this is sort of our maximum x value, and this is our minimum x value. And I'm going to label them 3 and -3 because we can see that the amplitude here is 3. So we have our amplitude here, and we found that our period is equal to 1. So that means in 1, it should go all the way up and all the way back. Okay, so we can divide this into half and then into quarters because that's where our little special points are going to be, because 1/4 of 1 is just a quarter. And we're starting all the way to the left, so that's as far as we're going to go in the minus. So it goes cosine, we're going to go minus, plus, minus, plus, minus, plus, minus, plus, minus. So we can see here what this graph kind of looks like, okay? So that is the graphical method of solving this problem. And we can see the resting position is where x equals 0. Okay, so rest is here at our x-axis. And so we can see it happens 1, 2, 3, 4 times. So we hit rest at t equals 1/4, 3/4, 5/4, and 7/4 seconds. So that's the graphical way of solving it. We can also solve it algebraically. And this actually may prove to be a little bit more challenging. Okay, so what we have is we can think about cosine. So we have y, okay? So we want to know where at t equals 0, we know that x equals -3. -3 cosine 2 pi times t. So that's cosine of pi, which is, sorry, I'm just going to draw a little dividing line here, equals -3. So that's kind of our starting point. Okay, so what we can think of if we're going to do it without actually graphing the function is we can think about where that regular thing would go. So what we want to know is where does our x equal 0? So we're really looking at solving the equation 0 equals -3 cosine 2 pi t. So we don't know. The -3 doesn't really matter. We know that cosine of 2 pi t equals 0. Well, cosine equals 0 on the whenever the angle is on the y-axis. So 2 pi t has to equal pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2. Any of those y-axis angles is where our cosine is going to be 0. So if we take these and we divide them by 2 pi, we get the same solutions that we would get up here. And once you get to 9 pi over 2, that's going to be more than 2 seconds. So that's not actually the solution we are looking for. Okay? So the ball passes through the rest position right here at these, whether you do it algebraically or whether you do it graphically. Okay? Second example, we have a Ferris wheel with a radius of 25 meters that takes 90 seconds to complete a full rotation. The lowest position of the compartments is 3 meters from the ground. How can you model your height above the ground while riding using a cosine function? Okay, so we actually want to model the height, and then we want to use the function to calculate the height in meters above the ground of a passenger who got on the Ferris wheel at t equals 0 after 1 minute. Okay? Let's draw a picture. Okay, so we have our lovely Ferris wheel. Okay, and we know that the distance between the Ferris wheel and the ground is 3 meters. We know that this radius is 25. Okay, So what we're looking, because we're looking to draw a sinusoidal function, we want to know where our midline is. We want to know our vertical displacement. We want to know what our maximum is. So if this is 25, it's also 25 going up. So the top of the Ferris wheel here is going to be at 53 meters. So we're going between 3 meters and 53 meters. Okay, so let's take a look at what this might look like graphically. Okay, so we're starting at the lowest point, right? So if t equals 0, we want to start at the lowest point. So if we're starting at, if we draw in our, we're actually going to want to draw our x-axis down here because this entire thing is going to be above. This represents our y equals 0. Y is going to represent our height of the car. And then our t is going to represent how much time has passed. So we're actually going to be starting at our lowest point, which is 3 meters. We're going to go up to a high point of 53. If you have a graph like this, I'll be okay with the fact that you may be fudging a little bit what it looks like. Our midline is going to be halfway between these. So if we add these together and divide by 2, we will get the midline. And that midline is going to be at 27. Nope, 28. 28 meters off the ground. That is 25 above 3 and 25 below 53. Okay? We're starting at our lowest point, and we're going to go to our middle, and then our high point, then our middle, and then our low point. So we've got this graph here that kind of goes between 3 and 23. So we need to figure out all of our values. So here we're looking at this. We have y equals, so let's start with the easier ones. Our midline is 28. So that means since the midline is 28, that's going to be our d for our equation. We're going to be adding 28 meters to move from 0 to 28. Our amplitude is the same as the radius of the wheel. It's the distance here between a high point and the middle. That's our amplitude, and our amplitude is going to be 25 meters. Our phase shift, well, we're starting at a low point. So since we're starting at a low point, we don't really need a phase shift. We're going to make our amplitude negative 25 is going to be our A for our equation because we want to start with a negative cosine. Because a positive cosine would start at a high point, so if we just make it negative, the negative cosine starts at a low point. Okay? We've got our D. The only thing we might need now is there a B? And there probably is going to be a B. So we have our period is equal to 90 seconds. Okay? So if we know that our entire period is 90 seconds, that means we're starting here at a low point. That makes this 90. Okay? That means all of these points here are going to be divided 90 divided by 4. And 90 divided by 2 is 45. 45 divided by 2 is 27 and a half. Nope. This will be 22 and a half. So that's 22.5, 45. And then add 22.5, we get 67.5. And these are our different seconds, dividing this 90-second period into 4 equally. So our period is 90 seconds. Period is equal to 2 pi over b. So my b is going to be 2 pi over 90. So b is 2 pi over 90, which is going to equal pi over 45. And so when I go to write down my equation, we have h is equal to negative 25 cosine of pi over 45 t plus 28. And because I wrote a negative there, I don't have to worry about any sort of phase shift that we're dealing with. Now, if I want to use it for the second part of the question to figure out what the height of a passenger who got on the ground after t equals 0 at t equals 0 after 1 minute. So 1 minute is 60 seconds. So we're going to have to put, okay, we have to make sure that we're using we used 90 as our period, we have to use 60 as our input. So their height is going to be negative 25 times cosine 60 over 45 is going to cancel to 4 pi over 3. If we divide everything by 15, plus 28. So cosine of 4 pi over 3, we can even solve this without using a calculator. It's pretty exciting. So cosine of 4 pi over 3, that's one of our special angles. So 4 pi over 3, what quadrant is it in? It's in quadrant 3, and it's got a reference angle of pi over 3. So here, this is a 1. It's a negative 1, and this is 2. So cosine of 4 pi over 3 is negative 1/2. So this is equal to negative 25 times negative 1/2 plus 28. So half of 25 is 12.5, so this is going to be 28 plus 12.5, which is going to equal to 40.5 meters above the ground.